Hello and welcome to this lecture. In this lecture, we're going to look at a very important idea called conditional expectation. So, this is very closely tied to MMSE estimation. When you want to do minimum mean square error estimation, it turns out conditional expectation is the important concept. So, let's get into it. Okay, so here is first let me start by reminding you about joint and conditional distributions. Particularly, I want you to picture this. This picture is very good to have when you want to think of conditional things and all that. So, here is a picture of a joint PMF Pxy of x comma y. So, how have I plotted this? This is a 3D plot. I have values of x here and I have values of y here. So, from this picture you can see y takes 4 values 0, 1, 2 and 3. Okay. And then x takes many values. It goes from 0 all the way to 20, okay, right. So, 0, 1, 2, 3 for y and 0 to 20 for x. And then for every value of y, I have the PMF stacked up like this, okay. There is one color here, yellowish color for y equals 0, dark blue for y equals 1, green for y equals 2 and red for y equals 3, okay. So, this is a visualization of the PMF. And it's all stacked up nicely like this. You can see how this is. No, this is the value of Pxy of x comma y is this height at every value. Okay, and all adds up to 1. So that's the PMF. Good to have this picture. And always when you think of a two-dimensional PMF or a density, have this picture. For density, it will be a continuous sort of function, but have this picture in mind. So it will clear up a lot of confusion about these expressions. Okay. So, we know what marginals are. For marginals, what do you do for a particular value of x? If you want to find the marginal, you sum over Pxy, or keeping x the same, you sum over all values of y. Okay, that is the marginal of x. What is marginal of y? Marginal of y at 1, you just sum over all values of x, keeping y the same. Okay, so that way if you sum, you will get marginal of y. This way if you sum, you will get marginal of x. Okay, so that is the marginal. What about conditional? You pick one particular value x, okay, and then of course, probability of that has to be greater than 0. Okay, so that's the value you're picking. Okay, and then the conditional distribution of y given x equals x naught of y is basically defined as the joint PMF of x naught comma y divided by the marginal of x. So, if you fix x naught, particular x naught here, and then look along this line, you sum it up, you get the marginal, and then you divide the actual values by the sum, you will actually get a PMF, right? At that particular x naught, this Py given x equals x naught itself becomes a PMF, right? Because I am adding up all those guys and dividing by the sum. Okay, this denominator is the sum of all the numerators over all y, right? So, this guy is called the conditional PMF. We have seen this earlier also, but this is the conditional PMF of y given x equals x naught. And you can see this support of this PMF, the values where it will be non-zero will depend on y. Okay, so for all y where this is greater than 0 is interesting. Okay, so this is conditional PMF. Same thing you can do given y equals y naught also, a particular value of y. Let's say y equals 1 if you take, here is the joint PMF, you divide by the sum of all of that, you will get an actual PMF, that is the conditional PMF of x given y equals 1, and like that you can define for every possible value. So, these are joint PMF, marginal PMF, conditional PMFs. Okay, so it's an important thing to remember. So, when you want conditional distributions, you just replace PMF with PDF, summation with integration, and all these definitions go through. We have seen it earlier also. Okay, so this is a recap of joint and conditional distributions. Okay, here's an example. Let's just go through this example once again. This kind of example is nice to figure out. Okay, so here is a joint PMF. How am I visualizing it? I am visualizing it as masses at particular points. There are 8 points here, 1, 2, 3, 4, 5, 6, 7, 8. At each point, the mass is 1 by 8. For instance, here you have 2 comma 0 1 by 8, 3 comma 0 1 by 8, 0 comma 1 1 by 8, 4 comma 1 1 by 8, 1 comma 2 1 by 8, 0 comma 3 1 by 8, 3 comma 3 1 by 8, 4 comma 3 1 by 8. That's the 8 values. You can write it in a table if you like. I've just visualized it on the xy plane because sometimes it's easier to see, given conditionals are easy to see there. Okay, so here is an example. Supposing I want to look at x given y equals 1. So, y is 1, okay, y is 1, it's right there, okay. I want to given y equals 1, I want to look at the distribution of x. So, if you see this row, this along this x equals 1, that part, not row exactly, this is line, right, horizontal line. You have 2 points, y could be, x for y equals 1, x could be 0 or x could be 4. Those are the 2 points. But the probabilities here are 1 by 2, 1 by 2. Remember, it's not 1 by 8, 1 by 8. A lot of people get confused. They think the conditional distribution is 1 by 8, 1 by 1 by 8, 1 by 8 is not valid, right? It doesn't add up to 1. So, given y equals 1, y is only 1. So, these two have to be normalized. So, you take 1 by 8 divide by the sum. Okay. So, 1 by 8 by 1 by 4 will become 1 by 2. So, you get 1 by 2 for 0, 1 by 2 for 4. Okay, I hope you see this. So, this distribution is very clear, right? X given y equals 1 takes only two values, 0, 4. X itself takes many values, no, 0, 1, 2, 3, 4. But given y equals 1, x takes only two values, 0 and 4, and with probabilities half and half. Okay. The other one you can see is x given y equals 3. If y is 3, x takes three values, 0, 3, and 4, all with equal probability, no? That's the main thing, all with equal probability. So, it will be 1 by 3, 1 by 3, 1 by 3. Okay, 0, 3, 4, 1 by 3. So, likewise, you can also do y. Y given x equals 1. So, if x is 1, y takes only one value, y becomes a constant. It's 2 with probability 1. Y given x equals 1. Y given x equals 3 is two values, 0 and 3 with probability half each. Okay. So, you can see this is very easy to do once you visualize it in the x and y given a particular value. The other things are very, very easy to visualize. Okay. Now, if you have a joint PDF, again the same PDF, we are taking uniform in this triangular area, height is 1, right. Now, I may want to think of a particular value of x, particular value of y. Let us say y naught now is between 0 and 1, a particular value here, and then you take a horizontal line like this. Okay. You take a horizontal line like this, you notice that x given y equals y naught is going to be uniform. Okay. Wherever it cuts is going to be uniform because the height is anyway flat. Now, if you divide and then all that, it's going to be flat, right. So, that's the important thing to realize. So, if you go to a particular y naught, x takes values from 0 to 2 times 1 minus y naught. We saw that earlier. So, in fact, given the flat nature, it will be in fact uniform. Okay. So, that's the nice thing about this density. You don't have to do any calculations, no need to integrate and all that. You see that x given y equals y naught is uniform from 0 to 2 times 1 minus y naught. I hope you see this. In case you want a quick explanation, this is just a blown up version of that, right. So, 1, 2, so you have y naught here, this is x is 2 times 1 minus y naught, 0. So, given y is y naught, x takes values from 0 to 2 times 1 minus y naught. But if you look at the conditionals, okay, so as x varies, this is always flat, which means this will be uniform. Okay, so the denominator is some value, it does not matter what it is. The numerator does not change with x, no, so it is flat. So, you end up getting uniform. Same thing for y also. Okay, so that is the idea here. So, x given y equals y naught is simply uniform from 0 to 2 times 1 minus y naught. So, same thing you can do for x. So, x goes from 0 to 2. So, 0 less than x naught less than 2. Y given x equals x naught, so, right, for particular x naught, y goes from 0 to 1 minus x by 2, right, sorry, 1 minus x by 2, right. So, given x equals x naught, y goes from 0 to 1 minus x naught by 2, and that is all uniform, isn't it? Since it's uniform, it becomes uniform distribution from 0 to 1 minus x naught by 2. Okay. Now, if you have an arbitrary joint PDF, it won't be uniform, it will have some other shape, but you can always calculate it. You can calculate the PDF of y given x equals x naught. You can calculate the PDF of x given y equals y naught. Okay. And from there, figure out the distribution and all that. Okay. So, this calculation you have to be comfortable with. Given different types of joint PDFs, you should be able to compute the conditional PDFs given particular values for one of the two random variables. Now, we have always seen the most important and interesting random variables are Gaussian random variables. Okay. So, once again, I am going to take Gaussian random variables and show you how to find the conditional distributions. This is very, very important. The most important distribution in all of electrical engineering is Gaussian. So, when you do conditional expectation or conditional distribution, you should be very comfortable with conditional distributions of Gaussians and conditional expectation. Okay. We have already seen a lot of ideas about Gaussian. So, I am going to go quickly through how it works. X and y are jointly Gaussian. I am going to take standardized values. So, x is normal 0, 1, y is normal 0, 1, and rho is the correlation coefficient, expected value of xy. Okay, the correlation coefficient. This is the description of the joint density. So, the joint density will be 1 by 2 pi root 1 minus rho squared e power minus x squared minus 2 rho xy plus y squared by 2 times 1 minus rho squared for all x and y. This is the joint density. Okay. So, now I have to find the conditional density. So, how that works is you have to divide the joint density by the marginal. But you can also do it in a different way, in a smart way. See, I know the marginal, right? The marginal of y is e power minus y squared by 2, 1 by root 2 pi e power minus y squared by 2. So, if I divide by that, I will get this, but you can also do it in a sort of interesting way to get the answer directly. So, notice what I am doing here. I am going to replace this y squared with rho squared y squared plus 1 minus rho squared y squared. I did not change anything, I just added rho squared y squared and I subtracted minus rho squared y squared. So, I got plus rho squared y squared plus 1 minus rho squared y squared. Why did I do this? You will see once I do this, I can split this sum. Okay, I can look at the first part separately, second part separately. Second part, if I separate, I get minus y squared by 2, which is what I wanted, the marginal, right, minus y squared by 2. The first part is nice also, it becomes just x minus rho y whole square. So, that is what I am doing here. Okay. So, I get 1 by root 2 pi e power minus y squared by 2, and then I get 1 by root 2 pi root of 1 minus rho squared e power minus x minus rho y whole squared by 2 times 1 minus rho squared. So, you notice here very easily you identify this with fy of y, and fxy of x comma y divided by fy of y is nothing but fx given y equals y. So, the conditional distribution of x given y equals y for a 2D standard Gaussian ends up being this expression, and if you stare at this expression close enough, you identify that this is nothing but a Gaussian density. Okay. This is a Gaussian density with mean rho y and variance 1 minus rho square. Okay. So, this is a very, very, very important result for 2D Gaussian standard, or soon we will extend it to non-standard. For jointly Gaussian random variables, the conditional distributions are also Gaussian. Okay. This is a very important fact to remember, and I have just shown it for you. And for the standard case, when n is 0, 1, 0, 1 and rho is the correlation coefficient, it is very, very easy to even remember the conditional distribution. X given y equals y is simply normal with mean rho y and variance 1 minus rho square. Okay, very, very easy to remember. Okay. So, I can do the same calculation for y given x equals x. Okay, everything is symmetric here. If I just split it on x instead of y and do the same calculation, you will get y given x equals x is also normal, now with mean rho x and variance 1 minus rho square. Okay. So, this is a very easy calculation to do. So, both conditional distributions are Gaussian. Mean is rho times x or rho times y depending on what you are conditioning on, and variance is always 1 minus rho square. Okay. So, it is a very nice thing to remember. In particular, if x and y are independent, if rho is 0, you notice that the conditional distribution becomes same as the marginal distribution. Okay. It is a nice thing to know. Okay, let us visualize. This is a visualization. In the previous case, I had a very easy visualization of the joint PMF and all. So, here I am going to do a slightly different visualization. Notice what I am doing here. I am visualizing the fy of y here. This is a Gaussian shape, right? Normal 0, 1. Okay, so this has a fy of y I have put here. What I have put here is the conditional density. Okay, x given y equals y for rho 0. When rho is 0, for every value of y, I am going to get the same n01, right? Notice I am getting the same n01, different colors. Y is minus 2, minus 1, 0, 1, 2, whatever value you take here, you are going to get the same n01. Okay. If you multiply these two, you have the Gaussian density. Remember, y has the jointly two-dimensional Gaussian density. So, you have fy of y here, all these conditionals, they multiply together to give you the combined joint PDF. Notice I have drawn this dotted line here, joining all the means here. These are this is the rho y, okay, right? This is rho y. All of them are 0, okay, because rho is 0, so it becomes 0. And then this is just to show you where the peak is, right? Just to show you how that works. Okay. So, this is a picture for rho equals 0. Now, what happens when rho is different? Suppose rho is 0.5. Notice what happens here. You've got the fy y here, okay. Okay. Is that all right? So, you have fy of y being always the same. Y is always n01, right? Nothing changes with that. What changes, if you notice, is where the peaks occur, okay. So, if you notice here for rho equals 0, all the peaks occurred at x equal to 0 for all the conditionals. So, here that is not what is happening, they are stacking up differently. The peaks do not occur at x equals 0, they occur at x equals 0.5 y. This is that line, this dotted line here that has the peaks. They all occur at 0.5 y, but the heights will be the same, right, because the variance is the same, 1 minus rho squared, right, 1 minus rho squared is the variance. So, the heights will be the same, but however, the peaks are aligned differently. So, it will sort of twist a little bit in the shape, but of course, you have to multiply by fy y if you want the joint PDF. So, it will have a different type of shape. Okay. So, this is important picture to see. What happens when rho is negative? Rho is negative, it goes this way, okay. X equals minus rho y, right, minus 0.5 y, I am sorry, it's rho y only, but minus 0.5 y. So, the peaks will line up a little bit differently, okay. So, the peaks will always be on the x equals rho y line, but because rho is negative, it will go this way, okay. So, let me switch between the three pictures, hopefully you will get a sense of it. Rho is 0, all the conditional PDFs are lined up along x equals 0, rho is positive, all the conditional PDFs are lined over x equals rho y, so it's x equals 0.5 y, so the peaks are shifted, they are not on the same horizontal line. And then if you go to rho negative, they line up like this. So, this is a good visualization to have for the marginal and the conditional multiplying together to give you the joint PDF. Okay, so this is the standard case. Okay, so that is about conditional distribution. Now we are finally ready to do conditional expectation. Okay, so this is not very hard. You have jointly distributed random variables. We already know the conditional distribution. So the expected value of x given y equals y naught is nothing but the expected value of x given y equals y naught. Okay, how do I do this? You just sum over all values of x times px given y equals y naught of x in the discrete case. What do you do for continuous? You integrate. Okay, so the expected value of the conditional distribution x given y equals y naught is the conditional expectation given y equals y naught. Expected value of x given y equals y naught. Expected value of y given x equals x naught. Okay, so notice what I am saying here. I am not calling this as the conditional expectation. It is basically the expectation of x given y equals y naught. Okay, it's very close to conditional expectation. There's one subtle difference when we do conditional expectation. It's mostly about notation and nuance. If you want to just think of this as conditional expectation, you're not too far off. Okay, it's okay. It's not too bad. But technically, there is one difference. I'll point out the technical difference soon enough. But this computation is the most vital computation. Given a particular y naught, you should be able to find expected value of x given y equals y naught. Okay, this computation is very important. Like that, given a value of x naught, you should be able to find expected value of y given x equals x naught. This is the first and most important part of the computation. So let us see a few examples of this. Let's go back to our example where we had the same discrete joint PMF. Earlier I had shown this example as well. Let's try and compute the conditional expectation. We saw x given y equals 1. It was 0, 4, half each. What is the expected value of x given y equals 1? It's 2, right? 0 into half plus 4 into half. Very easy computation, you can do 2. Likewise, x given y equals 3. It's uniform in 0, 3, 4. We saw that earlier. Expected value of x given y equals 3 is just multiply 0 times 1 by 3, 3 times 1 by 3, 4 times 1 by 3, 7 by 3. Okay, likewise you can compute. Okay, so given the conditional distribution, the conditional expectation is very trivial. In fact, in this particular case, given y x is equal to 1, y takes only one value. So clearly expected value is also the same. And you can also sort of graphically compute, no? Supposing you're given y equals 0, expected value of x is going to be between 2 and 5, 2 and 3, right? So it's going to be 2.5. Okay, so if you're given, I don't know, y equals 4, right? If you, x equals 4, y takes value 1 and 3 with probability half each. So expected value will again be 2. Okay, so like that you can easily visually compute the expected value. Okay, so this is an important thing. This is a simple distribution, but supposing you had Poisson and something else and all sorts of geometric and all that, it's a computation you have to do. Okay, so but the definition is very simple. The conditional distribution and its expectation is what you have to be able to compute. So let's do the same for the PDF case. Okay, the PDF case is also very, very easy. So we saw that x given y equals y naught is uniform 0 to 2 times 1 minus y naught. So what's the expected value? It's just 1 minus y naught, right? So it is a plus b by 2, no? Uniform distribution. So you get 1 minus y naught. So likewise for 0 less than x naught less than 2, we know y given x minus x equals x naught is uniform in 0 comma y minus x naught by 2. Expected value is simply this 0 plus this 1 minus x naught by 2 divided by 2, it's just half minus x naught by 4. Okay. So these kind of computations you should be very, very comfortable doing. Okay. So, so this computation is easy. About what comes next when I define conditional expectation is that slight difference I was pointing out. So let me talk about it and then we'll go and look at some examples. What do I do when I define conditional expectation is the following. So you have x and y being jointly distributed random variables. we know how to compute expected value of x given y equals y naught. Expected value of x given y equals y naught, you simply sum over all these things and compute. I'm going to call this as a function g of y naught. Notice the subtle change in what I'm doing. This expected value of x given y equals y naught is actually a function of y naught, no? Think about it. If y naught changes, this value changes. So that function I'm going to call g of y naught, okay? Like even in the continuous case, you will get a g of y naught, okay? So either in the discrete case or continuous case, I'm going to define g of y naught as this function, okay? Now the expected value of x given y, which is denoted expected value of x given y, is nothing but g of y, okay? It's the random variable y transformed through this function g of y naught. So it becomes a random variable and it becomes a function of y naught, okay? Function of y, I'm sorry. This random variable is a function of y, okay? So this is the subtle difference, right? So most people really get confused by this difference. So what is expected value of x given y equals y naught? It is just one number. What is expected value of x given y? It is a random variable, right? So here is the difference between those two. Expected value of x given y equals y naught is a number and it depends on y naught. When you change y naught, that function changes. But y is a random variable, right? So if you think of expected value of x given y as a random variable itself, you get the conditional expectation, which is a random variable, along with the probability. The expected value of x given y naught, y equals y naught is only values. Along with the probability of y equals y naught, you get the conditional expectation. Okay, so I'll give you an example and write this down. But notice the subtle difference between the value for a particular y naught and the random variable which captures the values for all y naught along with their probabilities. That's all is going on here, okay? So same thing you can do for expected value of y given x equals x naught, and here you will have a function h of x naught, and then I will define my expected value of y given x, not saying x equals x naught, as denoted as expected value of y given x, which is simply h of x, okay? So it becomes a random variable and it becomes a function of x now, okay? So one very easy way to remember is expected value of y given x equals x naught for a particular value of x naught is just one value. Now expected value of y given x is all values of x naught in a table along with the probabilities of x. So it becomes a random variable, okay? So that's the subtle difference. And let's see a couple of examples to drive that home. Same example as before, okay? Now, I have y naught taking values 0, 1, 2, 3, and I have a probability for them. And I also have expected value of x given y equals y naught. If y naught is 0, I just told you it's 2.5, and the probability is 1 by 4. If I collect all these values together, I get the expected value of x given y. Okay, instead of saying expected value of x given y equals y naught and the probabilities, all of that together, this entire table, if I want to capture in one notation, that is the notation expected value of x given y. In fact, how I would write it, notice what's happening. Expected value of x given y is the random variable which captures this table, right? So if I have u equals 1, 2, 7 by 3 and 5 by 2, probability that expected value of x given y equals u is this probability. Okay, but you don't have to worry about this right hand side table at all. It's just given there for just for completeness sake. Most people worry only about this table. Okay, this entire table together is called expected value of x given y. Okay, so think of it like that. Okay, for a particular value of y naught, you have only one value. Along with the probabilities, all the values together, this entire thing is sort of captured as expected value of x given y, and you can see readily it's a random variable. Okay, that's the idea. The same thing you can repeat for x also. So for every x naught equals 0, 1, 2, 3, 4, I have an expected value of y given x equals x naught. But x naught is a random variable. X naught takes different values with different probabilities. So if you capture all of them together, you get expected value of y given x as a random variable. This is the random variable, and you can see here this expected value of y given x is actually a function of x, right? It's a function of x, and if you put all of them together, it only takes three values: 0, 3 by 2, half. It takes value 0 with probability 1 by 8, 3 by 2 with probability 1 by 4, and 2 with probability 1 by 4 plus 1 by 4 plus 1 by 8, and that's 5 by 8. Okay, that's all. So you can think of this x given y and y given x as random variables which capture all of this information together. Okay, so that's important idea here. So let's continue with our continuous example for this conditional expectation. We had this uniform example before. We computed these conditional expectations. So what do I do to go from expected value of x given y equals y naught to just expected value of x given y? here is a very simple thing I'll tell you. Wherever you have y naught, simply replace it with capital Y. Okay. So here is my magic, and then that transforms from expected value of x given y equals y naught to expected value of x given y. So equals 1 minus y. That's it. Okay. So same thing with y given x. Y given x equals x naught is half minus x naught by 4. Simply replace x naught with capital X and drop the x naught here. You get expected value of y given x. So notice here in the continuous case, it's sort of very nice. You can see that expected value of x given y is a function of y explicitly, because we didn't have tables and all. No, the function is easier to see. Expected value of y given x is half minus x by 4. It's a specific function of x. Okay. So this is the form in which people understand conditional expectation. Okay. So hope you can see this. In fact, you can find the density of x given y and y given x, right? Expected value of x given y and expected value of y given x, their densities you can find. It is just 1 minus y. It's a function of y. Likewise here, half minus x by 4, it's a function of x. You know how to find the density of the of half minus x by 4 given the density of x, and that's all you have to do. But usually these are never ever needed. Okay, so you will see later on, you never have to find density of these things. It's not so important. So you can be, you can just, knowing this function is what's most important in practice. Okay. Okay, so let's close with the Gaussian examples. The Gaussian examples are very, very, very important, like I mentioned. Once again, the 2D standard Gaussian example I'll start with. So in this case, we know x given y equals y naught is normal with mean rho y naught and 1 minus rho squared, and we have calculated that expected value of x given y equals y naught is simply rho y naught. Now we replace, just drop the y naught everywhere and replace with y, so you get expected value of x given y is rho y. So a moment's thought will tell you that this is also Gaussian. This is actually normal with mean 0 and variance rho squared, but this sometimes is needed. We'll see later on when it's needed. Okay. So likewise, you can also do y given x equals x naught, and this is also normal. So expected value of y given x also becomes rho times x, which is again normal 0 and rho squared. Okay. So here is an illustration once again to just to show you expected value of y given x will be linear. Okay. So this line, right, rho times x captures the expected value of x given y and y given x. Okay. So quite often we may have to go to general Gaussians. Okay. So standard Gaussian was very, very easy, but you may want to go to general Gaussians, normal mu x sigma x squared, y normal mu y sigma y squared, and the correlation coefficient is rho xy. So in that case, what do? You convert to standard, right? So always the trick is to convert to standard. You go to x tilde, which is x minus mu x by sigma x, y tilde is y minus mu y by sigma y. Both are normal 0, 1, and the rho remains the same, right? The correlation coefficient remains the same. When you do linear operations like this, it doesn't change. Okay. So given x equals x naught or x tilde equals x 0 tilde. What is x 0 tilde? Is x 0 minus mu x by sigma. Expected value of y tilde given x tilde equals x 0 tilde is rho xy times x 0 tilde. We know that. Now we replace all the tildes with the originals. What do you get? Y minus mu y by sigma y given x equals x naught is rho xy times x naught minus mu x by sigma x. Now here you have to manipulate, right? I want only y, so I have to multiply by sigma y and then bring the mu x to the mu y to the right. These are all constants, no? This expectation doesn't affect them. So you go there and you will get this. So you see that expected value of y given x equals x naught is mu y plus rho xy times sigma y by sigma x times x naught minus mu x. Okay. This is a nice formula to sort of remember. In fact, you can put all these things together and you see that the conditional expectations are linear for the general case also, except it's not as simple as rho times x and rho times y. It has other factors coming in because sigma x and sigma y are there. Okay. The formula itself is reasonably easy to remember. Some people remember this by heart. Expected value of y given x is mu y plus rho xy sigma y by sigma x times x minus mu x. Okay. Now, if you want to find the density of this, you see that it's also Gaussian, it's normal, and it has a certain mean, and the mean is, so if you do expected value, what happens? X itself has expected value mu x, so this part will go away, right? Is that correct? You will only end up with mu y. So expected value of this guy is this is normal with mean mu y, and variance is this guy square, right? Rho xy sigma y squared. So the other constant terms won't show up in the variance. Only the thing multiplying x is important. The variance is sigma xy, rho xy squared, sigma y squared by sigma x squared. Okay. So this is something to remember for expected value of y given x. Sometimes it's useful later on in computations. Okay. So the most important thing is for Gaussian 2D Gaussian jointly Gaussian random variables, the conditional expectations become linear in x. Okay, they are linear functions of x. The expected value of y given x is generally a function of x, but for the 2D Gaussian case, it becomes a linear function of x. Okay. Okay, so the final thing I'm going to do is conclude with some properties. We won't discuss these things in great detail, but I'll just conclude with them. First thing is, if x and y are independent, then expected value of y given x is expected value of y, expected value of x given y is expected value of x. Okay? The conditioning doesn't matter. And then there is something called the Tower property, which is very, very crucial. We didn't see it, we're not going to use it too much, but you should know that expected value of y given x is a random variable, it's a function of x. What will happen if you take expected value of that guy? Expected value of this is actually expected value of y. This is called like sort of a Tower property, right? If you want to find expected value of y, you condition on x, but then you take the conditional expectation and then one more expectation around it. Same way around x also. I'm not going to prove these results, but this is a very important property. Quite often in calculations, this is very, very useful. The final property we saw is jointly Gaussian. If you have a jointly Gaussian situation, expected value of y given x is ax plus b, expected value of x given y is a linear function cy plus d. Okay, so that concludes conditional expectation. It was slightly longish lecture, but I think it's a very important idea. You have to get your handle on computing conditional expectations very, very easily. In particular, the 2D Gaussian case, you should be really, really comfortable computing conditional expectation. Pretty much all applications involve computing conditional expectation for 2D Gaussian case. Okay, thank you very much.